we're going to be taking a look at an activity that you did not get to do this year because we're not in class. Before I go to the next slide, I want to make sure that you guys know what a scatter plot is. It's where you simply just plot a bunch of points based on their coordinates. This is the activity that we're not going to get to do. If we start thinking of properties of humans, we can come up with a bunch. Height, weight, hair color, eye color, how long your nose is, and there's a lot of different properties that we can come up with. What causes all of these properties? 99% of them is caused by DNA. So the question that we would ask in class is, how can the relationship between the size of somebody's foot and their height be graphically represented? So you guys would go over, you'd measure your height with a meter stick, you'd measure your foot with either a ruler or a meter stick. You would then come back and you would plot your particular point based on your height and based on how long your foot is somewhere on this particular graph, which would be up on the screen. I'd give you a sticky note and you would figure out where you belong somewhere on this graph. Amazingly, I've done this for 5 years, 6 classes per year. That is 30 classes, and every single one fits this exact correlation perfectly. I mean, you might have a couple sticky notes in different places, but it is always this line right here. After that graph is done and we take a look at it, we try to figure out if there's any relationship based on the data that we see. Can we say that somebody's height causes them to have a certain size foot? Or can we say that your foot causes you to have a certain size height? Would we say that that is a positive correlation or a negative correlation? Well, this is positive. As the height gets bigger, the length of that person's foot is going to also get bigger. There is a reason why people that are taller have bigger feet. It has to do with the DNA. A few questions for you guys. Do you know of any way to come up with properties of stars? Like maybe their magnitude or luminosity, their color, their temperature? Do you guys know how to make a scatter plot? If you guys know how to make a scatter plot, do you also know how to analyze the data that you see in that scatter plot? The answer to all of those should be yes. Yes, you know how to do them. What we would do next is I would give you guys a bunch of data, and there's a bunch of different stars with their temperatures and their luminosities. It would be up to you guys to plot these different stars based on their temperature and their luminosity. I'm not going to make you do that, but here's what it would look like once we are done. You'll notice that there are a number of reddish stars down in the bottom right. There's some orange and yellow stars kind of in the middle. There's some blue stars as we get up in this direction. There's some red stars in the upper right hand corner, and there's kind of like a curve. What you guys would have produced, and every class prior to this has produced, is what's known as a Hertzsprung-Russell diagram, which is the most important chart in all of astronomy. If you ask what the most important chart in chemistry is, hopefully you come up with a periodic table. Well, an HR diagram is the most important chart in astronomy. Where does the weird name come from? Well, Anja Hertzsprung was a German astronomer. This is him next to Mr. Schwarzschild, which we will get to later in the year. Schwarzschild is the guy who first solved Einstein's field equations and came up with the size for an event horizon for a black hole. But this is Hertzsprung right here, and then Henry Norris Russell. Both of them came up with this chart kind of independently. He was in 1911, he was in 1913, and so they named this chart after both of them. What does it do? It plots the magnitude or luminosity versus the temperature or spectral class, and this is what it looks like. The most important chart in astronomy. You're going to see this for the next couple weeks, so let's get familiar with it. You'll see that luminosity or brightness is over here on the y-axis. You'll also notice that this is a logarithmic scale. So 1, 10, 100, 1,000, 10,000. On the x-axis, you have the temperature or the spectral class. So temperature is down here, and I want you to notice something very important. The temperature gets bigger as it goes to the left. So down here is at 3,000. Up here is at 30,000. So it's opposite of what most graphs are going to look like. So the temperature gets hotter as you move to the left, and as you move to the left, you're going to get hotter stars. You're going to go from a red star to a blue star. This path right here is probably the most important thing that you're going to need to learn. This is what's known as the main sequence. A star is born on the main sequence and spends like 90% of its life just on the main sequence. So the sun is a main sequence star. It's right here on the main sequence. And later in the sun's life, it's going to swell up into a red giant. So the surface temperature is going to be cooler, but it's going to be brighter. So we're going to plot the sun up here. When the sun dies, it's going to be in a completely different place altogether. It will die as a white dwarf, and it will be down here. If you guys can read an HR diagram, you guys are going to be able to tell the luminosity class, temperature, spectral class, the lifetime of a star, the size of a star, how bright the star is. Here are different size lines. So the sun is 1 sun big, 1 solar radii. If you are up here, you're going to be 10 solar radii. If you're here, you're 100. Here's 1,000. So Betelgeuse is about 1,000 times bigger than the sun. Down here is 100th. So you can tell the size of a star simply by plotting it on the HR diagram. You don't have to go out and measure it anymore. We have so many data points that if you know the temperature and absolute magnitude, you plot it on the HR diagram, and this will tell you the size of that star. Here we have an HR diagram with the sun on it, and you'll notice the sun is a main sequence star. I can add a new star. Depending on where the star is on an HR diagram, you will be able to tell some information, such as temperature, luminosity, size. You'll notice that as you get to a red giant, you get quite large. White dwarfs are very, very small. Main sequence, the very hot main sequence stars are pretty big. So how do we go about making these? Well, here you go.
This is a Hubble Space Telescope image of the crowded core of the globular cluster Omega Centauri. The brilliant colors of the stars are real. They correspond to stellar temperatures. They can also be used to trace stellar evolution. Astronomers like to know how blue the blue stars are and how red the red stars are. So we'll first sort these stars out by color, blue on the left and red on the right. Next, we'll sort the stars according to brightness, the brightest stars at the top and the faint stars at the bottom. The final plot you see represents different stages of evolution of stars. Stars spend most of their lifetime burning on the main sequence. When the fuel starts to run out, they expand to become red giants. They find a new source of fuel, helium, and burn blue hot. But even that runs out. They end up burning out as white dwarfs. Based on images for the Hubble Space Telescope, we've assembled a true plot that is a snapshot of the life history of stars in this ancient cluster.
So what this is basically telling us is that if we have a bunch of stars in the sky, we literally measure how bright they are and how hot they are, and we plot them on a graph. We make a scatter plot. No matter where we look in the sky, whatever group of stars we choose, we always get the same looking scatter plot. And the more data points we have, the more confident we are that every single star in the night sky is going to fit somewhere on this HR diagram. 90% of them are going to be right here in the main sequence. Towards the end of a star's life, it's going to end up here as a red giant. It's going to end in different places, but every star can be plotted on the HR diagram. HR diagrams also come in a number of different formats. So this one looks a little bit different than the one that I showed you originally. Has a little bit of different information. It's missing these lines here. But then you can have some that don't have those lines at all. You should still be able to recognize this as an HR diagram though. Here's one with thousands and thousands of stars plotted on it. And you will notice that here's the main sequence. Here are the red giants about to die. Here are white dwarfs. There are no stars that exist that are at this temperature and this brightness. They don't exist. You're never going to find a star that would go right here on the HR diagram. Some of them have a little bit less, some have a little bit more. All of them though are going to give you the same information. This one has brightness, first temperature. This one has spectral class. It's got magnitude and luminosity over here. These luminosity classes, we're going to go into them a little bit more tomorrow. These are the Roman numerals that we talked about before. The sun is a main sequence, which is Roman numeral 5, or V. We're going to get into that tomorrow. There's also something on this one that is not on some of the other ones, and that's this instability strip. First, I want to point out, before I talk about this instability strip, that this is not a map of where stars are located. This is simply a plot based on their characteristics. So the sun, as long as it's putting out the same amount of light and staying the same temperature, it will never move. Not until later on, when it grows into a red giant, is it going to move places on this HR diagram. Stars stay put for the most part once they're plotted, with a few exceptions. If you are what's known as a variable star is going to get big and cool, and then it's going to shrink, and that's going to get big, and that's going to shrink. If you're a variable star, you actually change your brightness and your temperature over the course of days or weeks. As you're changing your temperature and your brightness, you're going to be plotted in different places. So Henrietta Swan Leavitt studied. It's how we figure out how far away things are, because how fast they pulsate tells us how bright they are. So if we can figure out how bright they're supposed to be versus how bright they look, we can figure out their distance. So variable stars are very important for astronomers, and they all live right here in this instability strip, where sometimes they're bright, sometimes they're dim. So they do not stay put on the HR diagram. Some of them are very minimalist, but I hope by now you could already point out where the white dwarfs are. You could already point out where the red supergiants are, where the main sequence is. If I asked you guys on a test, count the red giants on this, would you be able to do it? If I asked you on a test to point out the main sequence, hopefully you'd be able to do that already. These names are their luminosity classes, which are the Roman numerals. This one's my favorite. It's got just about everything. It's got temperature, luminosity class, absolute magnitude, it's got luminosity, it has their color, it has their size, it has these size radii lines, it has their spectral classes right here in the middle. The stars are different sizes based on how big they are in real life. This one's probably my favorite one that I found. Some of them are going to be really, really easy to read, and this one, weirdly, is backwards. So this one has cold stars on the left, and it gets hotter to the right. 99% of the time you're going to see it the other way. So this main sequence looks like it's going up in this direction because it's going from cold to hot as it moves to the right. Most of them are going to be completely different. This one has something brand new for you. OBAFGKM. OBA, fine girl or guy, kiss me. What the heck is L and T? An L class star? A T class star? Those are brown dwarfs. We're going to get to that tomorrow. Is a brown dwarf a star? I don't know. We'll get there. Just so that you know, anything can be plotted on an HR diagram, as long as it has a brightness and a temperature. So you could plot a candle on an HR diagram. As long as these objects have a temperature and you can see them, they have luminosity, you can put them on an HR diagram, which is what they did for this one.
The secret of the stars. It's a beautiful piece of science. It's a beautifully elegant theory. It's a beautiful piece of science. It's a beautiful piece of...